let f of t is a deterministic signal, then integral minus infinity to plus infinity e power minus j omega t dt is called as the Fourier transform of the deterministic function f of t, and this is denoted as f of omega. The sufficient condition for existence of the Fourier transform is what is the sufficient condition for existence of the Fourier transform? The function f of t must be absolutely integrable. And also the function must be square integrable. See, there are some functions, they are absolutely not integrable, but their square is integrable. That is, some functions like, if you consider the sinc function is not absolutely integrable, but the sinc function is absolutely square integrable. That is the difference. So that's why here we are letting the f of t is absolutely integrable and it is square integrable. So what this quantity indicates, this is the energy, is it? So the signal must be of finite energy. So therefore here we are letting this f of t is an energy type of the signal, and that is absolutely integrable and its energy is finite. Follow? Now we let this x of t is a random process, and x of t is one sample function of the random process. We already know that x of t, capital X of t is the collection of the sample functions. So one sample function of the random process is given by x of t. So you should clearly distinguish the capital X of t and the small x of t. Capital X of t is the random process, the small x of t is the sample function. Here we are defining a function xt of t that is equivalent to x of t for minus t less than or equivalent to t plus t. That is, over the interval minus t to plus t, this xt of t is equivalent to x of t. That is, we are truncating the sample function and getting the sample function over the interval minus t to plus t. So that we are denoting it as xt of t. Xt of t is equivalent to the sample function over the interval minus t to plus t. And let it be 0 otherwise. Then the Fourier transform of this xt of t can be written as integral minus t to t xt of t e power minus j omega t, is it? So this can also be equated to minus t to plus t. This is, see, in the interval minus t to t, xt of t is x of t. And denote this as xt of, so xt of omega is the Fourier transform of xt of t, which is equivalent to minus t to t x of t e power minus j omega t. Actually the integral is from minus infinity to plus infinity, but from minus infinity to 0 and 0 to t to infinity it is 0. So that's why we are writing it as minus t to t. You can split this term minus t to t, minus infinity to minus t, and minus t to plus t, t to infinity. The two extreme integrals will become 0, and the only integral is this minus t to. If you let Et is the energy content of the signal xt of. So that can be written as integral minus t plus t whole square t. Is it right? What this indicates? This is the energy content of the function xt of, energy content of the sample function for the interval minus t to plus t. This can also be written as integral minus t to plus t x of t whole square. Why? Because in that interval this xt of t is equivalent to x of t. Is it right? Can I write this as 1 by 2 pi integral minus infinity to plus infinity is it right? What this indicates? It's a Parseval's relation. That is, if you transform the function from time domain to frequency domain, its energy content will not change. The energy content of the function xt of t over the interval minus t to t is equivalent to this. In the frequency domain, see, we already know this. We already know the Fourier transform of the xt of t. Therefore, we can also find the power in the frequency domain as 1 by 2 pi minus infinity plus infinity mod xt of omega whole square d omega. See the integral limits here. See, these are not minus t to t. Why? We are integrating with respect to omega. This is in the frequency domain. This is in the time domain. That is the difference. So this is minus t to t mod x of t whole square dt. This is the energy of the signal. This is also the energy of the signal. So according to the Parseval's theorem, this integral is equivalent to this. Is it right? Find the average power. So if you let the average power as the P average, that is equivalent to energy by time. So here we know the energy or the interval minus t to t. So therefore, you divide that energy with that duration, you will get the average power. It is the time average, which is equivalent to integral minus t to plus t, and this is 1 by 2 t whole square dt. Is it right? So which can also be written as 1 by 2 t, this is minus t to t mod x of t whole square. Are you following? So this can also be written as 1 by 2 pi into 1 by 2 t, so minus infinity to plus infinity mod xt of omega whole square d1. Is it clear? This can be written as 1 by 2 pi. So minus infinity to plus infinity. You bring this 2t inside, then we can write it as mod xt of omega divided by 2t t1. So this is the T average. Is it clear? Average power of xt of t. Average power of xt of t is equivalent to integral 1 by 2 times minus infinity to t mod x of t whole square dt, which is equivalent to 1 by 2 pi integral minus infinity to plus infinity this square divided by 2t into d1. Understood this? So here we consider the random process and one sample function x of t. This sample function is observed or is considered for the interval minus t to t. So this is the average power of xt of t over the interval minus t to t, or average power of x of t over the interval minus t to t. If you want to find the average power of the entire signal, then you have to consider the entire interval. So for that purpose, you can simply take this t is taking values from minus infinity to plus infinity, like t is tending to infinity. So if t is tending to infinity, then this average power will be of the entire sample function, that is from minus infinity to plus infinity. So first we obtain the average power of the sample function from minus t to t. Now let t is tending to infinity, then it is the average power of the sample function over the entire interval. So we will continue in the next class.